In this video, we're going to focus on a different aspect of functions. So we've talked about defining them, evaluating them. We've talked about the difference between a function and a relation, how to find something that is a function or not. Now we're going to talk about something known as domain and range. We're going to talk about this in the context of a function. It works for relations as well, but we're going to think about it in the context of functions. So we said a function, so we said that a function was something that took an input, fed it into the function machine, and then it gave us an output, which we called f of x. So it had an input x, it had an output f of x, and then it had the function machine that turned the x into the f of x. Domain and range are concepts that relate heavily to this way of thinking about a function. The full collection of inputs, full collection of inputs is called the domain. So the collection of all possible x values that go into the function machine, that collection of values is what we call the domain. Domain is just another word for it. The full collection of outputs, full collection of outputs is what we often refer to as the range. So all of the possible values you can put into the function machine, values that the function machine will actually calculate, that's called the domain. All of the values that it can possibly spit out based on the numbers that went in, that's called the range. Now, in this video, we're just going to use these quite simple terminologies. We're going to say that everything goes in is the domain and everything comes out is the range. If you go on to study higher level mathematics, particularly mathematics that's geared towards, say, pure mathematics, you may start to encounter other terminologies such as codomain, inver-range. You may have a few other terminologies that deal with the collections of points that sit in a particular space, and they might not use the words domain and range. That's fine, that's great. But the way that we're going to think about functions and the way the advanced maths course thinks about functions is domain is everything that goes in, range is everything that comes out of a function. So often in domain and range questions, you will be asked to find the domain and range for particular functions. So you'll be given a function, and then you'll be told what's everything that can go into this, what's everything that can come out of this. So let's look at two examples. We'll look at one that's relatively simple, one that's a little bit more complicated. So the first example, we're going to say our function f of x is x, let's say it is x cubed plus 2x. So this is a cubic plus a linear. It's a cubic function with a linear term in it. If we think about this as a function machine, so we draw this in our little function box, x cubed plus 2x, x values are going to go into this, and then f of x values are going to come out of this. So to work out the domain, we need to say, well, okay, what values can go into this? Usually the question you're going to ask yourself is, are there any restrictions on the values that can go into this equation? Sometimes there will be, sometimes there won't be. So the x values, can we have positive numbers? Yes. Negative numbers? Yes. Zero? Yes. Fractions? Yes. Irrationals? Yes. So pretty much this takes every possible input. So the domain is all x. And in fact, it's all x, including the rationals and irrationals. So the domain is, here comes that double-lined R, this is the set of all real numbers. So it's a full domain. All possible values of x can go into this equation. The range, if we think about that, we say, well, okay, x cubed plus 2x. Are there any values that cannot come out of this equation? Well, you can put everything in. So can we get positive numbers out? Well, if x is positive, yes, because a positive cube plus 2 times a positive is a positive. And in fact, you can get any x no matter how large. Can we get negatives? Definitely, right? Negative cubed is a negative, 2 times a negative is a negative. So we can get infinitely many positive numbers, infinitely many negative numbers. Can we get 0? Yes, if x is 0. So the range in this case is actually all real numbers as well. So this is a function that can take in any possible x value, and it can spit out any possible f of x value. So it has a full domain and a full range. Now let's look at something that's a bit more complicated. Let's imagine f of x is 4 over x squared plus 3. So we're going to say, okay, our function box in this case is the formula 4 on x squared plus 3. The x values are going to go in, and then we're going to get f of x is out. You don't need to draw the function box every time. It's just a good way of thinking about it. Well, is there any x value that we can't plug in? It looks like we can plug in all positive x, because as long as we plug in positive x, the denominator's positive, numerator's positive, that should be fine. Are there any negative x values we can't plug in? Well, no, there aren't, because if you put a negative in here, it'll get squared, and that'll just become positive. So if you put in, -1, -1 squared is 1, 1 plus 3 is 4. So for this one, the domain actually ends up being all real values. You can put anything in. These equations sometimes have a limitation on the x value, because for a fraction, you can't have a denominator equal to 0. And that is something that you want to be careful of, right? You want to make sure, okay, can I make the denominator equal to 0 by putting in any x values? In this one, we couldn't. The range for this question is a little bit harder, though. We want to say, well, are there any values that we can't get out of this function? Well, sort of. Let's think about what this fraction is. This is 4 over a positive number. It's 4 over a positive number always. And in fact, the positive number can be as low as 3 and as high as infinity. So this fraction can take a value 4/3 or up. That's all though. It can't take anything below that, because for it to take a value, sorry, not 4/3 or up, it can take 4/3 or a number where the 3 goes up. So 4 or the 3 can rise. So it could be 4/5, or it could be 4 on 100, or so on. So if you keep making that smaller, it gets toward, if you keep making the denominator bigger, the whole fraction gets closer to 0. So this means this thing is actually bound between 0 and 4/3. At its biggest, it can be 4/3. At its smallest, it can be 0. And so that means we've got actually a restriction on the range. The range is f of x included in the set. This thing can't actually become 0. So it can approach 0 on the lower end. And then at the upper end, it can become 4/3. So this one was a little bit harder. The range was a bit more complicated to calculate because it's got a slightly unusual formula. So I'm going to give you 2 questions to have a go at. So question 1, question 2. I want you to find domain, DOM, and range for both of these examples. So the first one, you are going to be given x, y is equal to 4. And then for the second one, you are going to be given x squared plus y squared is equal to 16. Now, the second one is not a function, but we can still think about the domain and range. We're still thinking about the domain as all of the inputs, and we're thinking about the range as all of the outputs. If you can't think about the domain and range analytically, what you can do is you can try graphing it, and you can see the values suitable for x and y. So pause the video now and have a go. Good luck. Okay, so let's go through these. The first one, if we divide both sides by x, we end up with the formula y equals 4 on x. So to find the domain and range, we're going to graph y equals 4 on x. we'll draw a little picture of it over here. It's going to be what's known as a hyperbola, and it's going to have a slope associated with the number 4. So it's going to have a curve like this over here and a curve like this over here. This heads towards the x-axis, this heads towards the y-axis, this heads towards the y-axis, this heads towards the x-axis. So from the graph, and we label our x and y always on our axes, from the graph, we can see that the domain is actually going to be pretty much all x values. It just can't have an x value of 0. So it is going to be all real numbers, but x cannot equal 0. The range is going to be similar. The range, we can see you can have all y values, right? You can have whatever this y value is, whatever this y value is. No matter how high or low, you just can't have the x-axis, which is y equals 0. So the range, also all real values, but y can't be equal to 0. So this is the domain and range of the first one. Second one, we said this, x squared plus y squared equals a number, was a circle. And in fact, x squared plus y squared is equal to the radius squared of the circle. So 16 is 4 squared. So this is the circle of radius 4. So let's draw it. Kind of looks like this. This is 4, this is minus 4, and 4. What we are going to call the domain in this case is going to be all of the x values that can go in. Now, it's not a function, but we're going to use the domain and range terminology anyway, because that's pretty common in the advanced maths course. So the domain is all the x values. Well, we can see they go along here from minus 4 up to 4, including 0. So the domain is x included in the set minus 4 to 4. The range is actually the same, but y values. So the range is going to be all these y values from minus 4 up to 4, including those two. So the range will be y included in the set minus 4 up to 4, which we could also write as f of x. Well, sometimes we could write this as f of x included in the set minus 4 up to 4. This is not a very suitable notation in the case of question 2, because the thing that we're dealing with is a relation. A relation, not a function. In the first question, we could have said the range is R, but f of x can't be equal to 0. This was another way of denominating the domain and range. In the second one, we don't really need to do that because this is not a function, it's a relation. You will sometimes see the domain and range, even for relations, written using that f of x notation, though, just because it's quite common. So this is how we find domains and ranges.